Welcome back to the deep dive. So today we're dispensing with the high-level metaphors,
Yeah, we're going straight into the tensor operation.
straight into the tensor operations. Most of you listening are already well acquainted with standard adversarial attacks, tweaking pixels to flip a classification label. We've seen it with FGSM, with PGD.
Sure, the classic panda to give an example.
Exactly. But today, we're really escalating the problem space to semantic segmentation.
Which is a whole different ballgame.
It is. Specifically, we're digging into the SegTrans framework, presented by Yufei and their colleagues in IE Transactions on Multimedia. And this paper, it really goes after the holy grail of this research area.
Which is achieving high transferability. So attacking a model you don't have access to, a black box setting, but for segmentation.
It's a fascinating problem because fundamentally, segmentation models are just more robust than simple classifiers.
Oh, absolutely. In classification, you're just pushing a single probability vector across a line. But with segmentation, you're attacking a dense prediction map. You're trying to fool pixel-level classifications across the entire image.
All while keeping the scene structure somewhat coherent. It's a notoriously difficult optimization problem.
It is, and that's why this paper is so interesting.
Right. And its core contribution isn't just that it gets state-of-the-art results, but that it really diagnoses why previous transfer attacks were failing.
They pin it down to two main hurdles.
Tight coupling and feature fixation. So let's start with tight coupling. This gets at the inherent error correction that's built into these segmentation architectures.
Right, so, a standard classifier might just look for a specific texture or shape. But a model like DeepLab or PSPNet, it leans very heavily on contextual relationships.
It aggregates context to figure out the labels.
Exactly. The classic example they use in the paper is a person riding a bicycle. The model sees the pixels for the rider, and it uses that semantic context to sort of double-check and reinforce its classification of the bicycle pixels underneath.
So if you try to attack the bicycle pixels with a standard gradient attack,
the model just uses the clean, unperturbed rider context to go, nope, that's still a bicycle.
the context literally smooths out the adversarial noise.
And the authors actually proved this experimentally, which I thought was great.
Yeah, they didn't just guess. They took an image, ran a PGD attack, and the transfer success rate was, okay.
Pretty low.
Then they manually cut out the object, removed all the background context, and ran the exact same attack generation.
And the success rate shot through the roof.
It skyrocketed, which just confirms that this coupling between an object and its background is a huge buffer against these perturbations.
Okay, so that's hurdle number one. That brings us to the second one, feature fixation. And this is purely a surrogate model problem, isn't it? It is. In a black box attack, you're optimizing on a model you have access to, right? Let's say it's an FCN. But you're hoping the attack transfers to a target you can't see, maybe a DeepLab v3 plus move.
And those architectures are just worlds apart.
Completely different. An FCN, a fully convolutional network, it processes geometry pretty directly, but then you have DeepLab v3 plus Kier, and it's using things like a tetraphospatial pyramid pooling, dilated convolutions. It's built to capture multi-scale context.
And the paper's GradCam visualizations for this were so telling.
Oh, they were perfect. For the same input image, you see the FCN's heat map lighting up on, say, the wheel of a car.
But the DeepLab model is focusing on the windshield and the road.
Exactly. And that's feature fixation in a nutshell. If you craft your perfect attack to distort the wheel features that the FCN cares about, the DeepLab model basically just shrugs. It's looking at a different set of features entirely.
So the noise overfits the surrogate's architecture.
It becomes useless. So the whole mission for SegTrans is to solve these two things. Break the context to beat tight coupling, and generalize the noise to beat feature fixation.
All right, let's get into the methodology. SegTrans isn't really one algorithm. It's more of a framework with two main modules. The first one is called multi-region perturbation activation.
And this one is aimed squarely at breaking that tight coupling.
The mechanism is this clever grid-based masking strategy.
Yeah, the core idea is to shift the whole strategy away from using global semantic info. Instead, they want to leverage partial semantic info. So instead of finding the gradient on the whole image at once,
They chop it up.
they divide the image into little identical grids. In their final setup, they went with 1n16, so a 4x4 grid.
But it's not just the grid squares. Within each of those 16 squares, they select a random rectangular region.
Correct, and a $1 by $2 rectangle. And they generate a mask, which is defined in equation 6 in the paper, that basically blacks out everything except for these random little rectangles.
So during the attack generation, The model only gets to see this fragmented, disjointed version of the image.
Yes. It just sees these isolated patches, a little bit of tire here, a piece of the sky there, with none of the global context that connects them.
Which means the writer can't help the model classify the bicycle, because one of them might be completely masked out.
It forces the optimization to find a perturbation that works on a purely local level. The resulting noise has to be incredibly potent to fool the model when it only has this tiny, isolated patch of information to go on.
So that tackles the context problem. But what about feature fixation? We're still running this on an FCN surrogate, right?
Mm-hmm.
Aren't we still just overfitting to how an FCN sees the world, even if it's a fragmented world?
That's where the second module comes in. It's called semantic remapping.
Okay.
This is an iterative process. So a standard attack like PGD runs for a certain number of steps. SegTrans adds a little subloop. In each main iteration, it generates different enhanced images.
And enhanced here just means it applies a different set of random masks each time.
Exactly. It creates $2 different fragmented views of the same image. Then, and this is the key from equation 5, it calculates the gradient by summing the loss across all teller to dollars of those diverse masked views at the same time.
I see. So you're not optimizing against one static view of the image. You're averaging the gradient over a whole distribution of these fragmented views.
Precisely. It's like you're simulating architectural diversity. By forcing the perturbation to work across many different partial views, you stop it from getting fixated on any single feature that might be unique to the FCN surrogate.
It's almost like an ensemble approach, but you're ensembling the data transformations instead of the actual models.
That is a perfect way to put it. It decouples the attack from the surrogate's specific architecture and solves that feature fixation problem.
Okay, let's talk about the results. The experimental setup was pretty rigorous.
It was. They used PASCAL VOC 2012 and Cityscapes, which are the standard benchmarks here. And they used 4 different models: FCN, PSPNet, DeepLab V1, and DeepLab V3 plus V.
And crucially, they also mixed up the backbones. MobileNet, ResNet 50, ResNet 101.
Which lets them test everything, transferring from FCN to DeepLab, but also from a model with a ResNet 50 backbone to one with a ResNet 101. It's comprehensive.
And the main competitor was the previous state-of-the-art, EBD.
Right, EBD, which stands for Ensemble-Based Black Box Attack on Dense Prediction. And before this paper, that was really the only way to get decent transferability. You had to attack a weighted average of multiple models.
And SegTrans blew it out of the water.
It really did. The headline result is an average increase of 8.55% in attack success rate compared to EBD.
An 8.5% jump over SOTA is, well, that's not incremental.
No, that's a generational leap in adversarial research.
Wow.
And what was really notable was the consistency. The paper shows that it barely mattered which surrogate model they used.
So generating the attack on a simple FCN with a MobileNet backbone transferred almost as well as one generated on a heavy DeepLab model.
Exactly. Which is the empirical proof that their semantic remapping idea actually works. It really did decouple the attack from the surrogate's architecture.
We should also talk about computational efficiency, because EBD, being an ensemble method, must be incredibly heavy.
Oh, it's a huge drawback. You're running forward and backward passes on multiple giant networks for every single step. It's slow, it's resource intensive.
But SegTrans only operates on a single surrogate.
Right. It processes $2 masked inputs, but that's just a batch input to the same network. The authors report that it improves efficiency by over 100% compared to EBD.
Wow.
In terms of samples per second, it's running at speeds comparable to a standard non-transferable PGD attack.
That completely changes the threat model. It means you can generate these SOTA highly transferable attacks basically in real time on a single GPU. You don't need a model farm.
It lowers the barrier to entry for this kind of attack significantly.
Okay, but what about defenses? A powerful attack needs to hold up against some basic hardening. They tested against 3 things: adversarial training, pruning, and corruption.
Yep. And adversarial training is usually the gold standard for defense.
So how did SegTrans do?
Well, the performance did dip a bit, which you'd expect, but the attack was still highly effective. The mean intersection over union, the MIOU of the attacked images, stayed below 40%.
And for anyone listening, a normal MIOU on these datasets is in the 70s or 80s. Pushing it below 40% means the segmentation map is basically useless.
Utterly broken. So the defense helped, but it didn't solve the problem. The attack vector was still valid.
What about model pruning? The idea there is that by zeroing out redundant weights, you might remove the fragile parts of the network that attacks exploit.
That hypothesis did not hold up here. They pruned up to 70% of the model's weights.
70%.
And even as the model's normal accuracy started to suffer from being so sparse, the SegTrans attack was still just as effective. The ASR barely dropped.
Which suggests the attack isn't latching onto some weird, fragile feature. It's going after the core semantic features the model needs to function.
That's right. It's attacking something fundamental.
I want to dig into one of the ablation studies because I thought this was crucial, the black region validation.
Yes. This was a great control experiment. So a skeptic could look at this method and say, well, you're just introducing a bunch of sharp edges with your masks. Maybe the high-frequency noise from the mask itself is what's confusing the CNN.
A reasonable objection.
A very reasonable objection. So to disprove this, they ran a control where they used the same grid masking, but instead of keeping the image patches, they filled those regions with pure black pixels.
Zero semantic information. Just the mask boundaries and the adversarial noise.
Exactly. And the result, an attack success rate of about 2.76%.
Which is basically zero. It's just random noise at that point.
Completely. And this definitively proves that the attack relies on the partial semantic information inside those little rectangles to work. It's not an artifact of the masking, it's leveraging the object's actual semantics.
So to wrap this all up, SegTrans basically shows that the very things we thought made segmentation models robust, their reliance on context and feature aggregation, can actually be inverted and used against them.
It's a massive vulnerability. And the implications for things like autonomous driving are, well, they're significant. These systems use segmentation to find drivable road and to spot pedestrians.
And this paper proves an attacker doesn't need the car company's proprietary model.
Nope. They can just download a standard ResNet 50 off the web, train a transferable attack, and have a high probability of compromising the system in that car. It kind of nullifies the whole security through obscurity idea for these black box models.
It really forces a rethink of how we design for robustness. You can't just count on context aggregation to save you.
That process can be decoupled and exploited. We know that now.
I want to end on a forward-looking thought that came from the paper's discussion section. So we've established that training the attack on these partial, fragmented images makes the attack much, much stronger.
Right.
So what if we invert that? Could we use this same process, this multi-region perturbation activation, as a data augmentation technique while training our defensive models?
That's a really compelling idea. If you force a model during training to learn how to recognize a car based only on these tiny fragmented patches.
You're denying it the crutch of global context.
Exactly. You could potentially train a model that's not just robust to this specific attack, but to all sorts of other problems like occlusion or weird lighting.
You'd be forcing it to learn a much more fundamental feature representation that doesn't just fall apart when the context is messed with.
It suggests that real robustness isn't about seeing the whole picture. It's about understanding the constituent parts so well that the global context becomes a helpful signal, not a single point of failure.
That's a very strong takeaway. The paper is SegTrans, Transferable Adversarial Examples for Segmentation. It really represents a major step forward in understanding the vulnerabilities of these dense prediction models.
It's a dense read for sure, but I'd highly recommend it for anyone working in computer vision or safety assurance.
That wraps up our deep dive for today. As always, we will link to the paper and the code repository in the notes. Go check out the results for yourself, and we'll catch you on the next one.